Thank you for joining this talk. I'm Cenk Gündoğan, and together with my colleagues Christian, Thomas, and Matthias, we explore a RESTful information-centric web of things. In our paper, we progressively add information-centric principles to a common IP-based IoT deployment and investigate whether the benefits of stateful forwarding, caching, content object security, and location independence of data show similar performance results as they do for CCNX and NDN. The common Web of Things deployment consists of constrained IoT devices, a gateway with uplink connectivity, and cloud services. The IETF protocol suite uses the constrained application protocol CoAP on top of UDP to provide an end-to-end connectivity between IoT devices and the cloud. An end-to-end security is provided by DTLS, which is the Datagram Transport Layer Security. The CoAP proxy functionality allows for protocol conversions, for example from CoAP over DTLS to HTTP over TLS, and integrates a response cache to reduce the number of hop traversals for previously requested content. This has the issue of terminating security channels at the gateway itself, and the gateway now has to be included in the trust relationship between the IoT device and the cloud. OSCORE is the IETF solution to provide content object security for CoAP and enables an end-to-end security that goes beyond untrusted proxy gateways. We observe that standard CoAP features can enable information-centric properties, such as stateful proxying or forwarding, content caching, and content object security. In our opinion, having an information-centric Web of Things allows for an early deployment chance of many of the ICN principles and benefits in pre-existing IP-based IoT infrastructure. We therefore pursue two research questions in our paper. First, can we build a RESTful Web of Things with CoAP that also displays characteristics of an information-centric network? And second, would such a deployment yield similar network performance results as a pure ICN deployment in the IoT? In the remainder of this talk, I will focus on our approach of constructing an information-centric Web of Things deployment using standard CoAP features. I will then present our analysis that compares different integration levels of the construction phase to pure CCNX or NDN deployment. And then I conclude and draw the next steps for our future work. Let's first look at the protocol operation of a plain CoAP deployment. Next to other methods, it supports the request-response model using a GET method. The client sends a request and the server returns a response, which either contains an error code or the requested content. CoAP also allows to piggyback the acknowledgement for the reception of the request. CoAP supports optional reliability for messages. This means client and server endpoints configure acknowledgement timers, and if no acknowledgements are received during this time, then retransmissions are sent from the endpoints. We compare this plain CoAP setup against this list of selected ICN principles. The forwarding is handled on the IP layer and is therefore stateless. There is no caching on the intermediate hops involved. The data exists on the endpoints and is addressed using the server's IP port tuple and the CoAP resource name. And at best, this setup uses DTLS to secure the transport between endpoints, but not the content itself. We now construct a CoAP deployment that displays similar characteristics as a pure NDN deployment. First, we loosen CoAP's end-to-end principle by deploying a CoAP proxy on each hop along a request path. With this method, each request is addressed to the next hop proxy, and this proxy generates in turn a new request for its next hop. And this process repeats until the request reaches the origin server. Returning responses traverse the exact same request path from proxy to proxy towards the initial client node. This forwarding behaves very similar to the forwarding in CCNX and NDN with their pending interest table. Further, each proxy hop configures acknowledgement timers, so that each proxy hop triggers retransmissions on message timeout. And CoAP proxies also implement a response caching feature very similar to the CCNX and NDN. From previous studies, we already know that a hopwise caching can greatly improve the reliability by shortening the request path and reducing the amount of unwanted retransmissions. Since requests are addressed directly to the next hop proxy node, IP addresses can be linked local and do not point to the original content servers anymore. The forwarding is now handled by the CoAP proxy, and forwarding decisions are made using the CoAP resource name. In our evaluations, we will compare the two depicted setups, the first without caching and the second with caching, to a pure NDN deployment. We call the first setup CoAP minimum proxy and the second setup CoAP proxy. Now let's have a look at the security principle. The IETF provides OSCORE, the Object Security for Constrained RESTful Environments protocol, which is a proposed standard since July 2019. OSCORE itself builds on top of COSI, the CBOR object signing and encryption protocol, and inherits the authenticated encryption with associated data method. OSCORE provides confidentiality, integrity, a strong request-response binding, and non-replayability of previous messages. A potential problem with a strong message binding is that it prevents cache hits from subsequent requests, even if they originate from the same source. And this is a topic that we are currently trying to address in our ongoing studies. For this paper, we consider response caches to be retransmission caches in order to recover lost messages of the same transaction from hop to hop. We now have a deployment option at hand that uses standard CoAP features and displays information-centric properties. In our evaluations, we analyze different metrics that are relevant for operations in constrained IoT deployments. We perform all our experiments on real hardware using the IoT Lab testbed, which provides deployments on several sites across France. We use the M3 node as our hardware platform. It features an ARM Cortex-based architecture with 64 KB RAM, 502 KB ROM, and includes the 2.4 GHz-based 15.4 radio transceiver with basic MAC layer features. The IoT devices run the RIOT operating system with external packages, libOSCORE and CCN Lite, and we deploy our experiments on the depicted multi-hop topology. It includes 12 producer nodes and 11 forwarder nodes, and they statically arrange on a destination-oriented directed acyclic graph. For our experiments, we consider a converged cast scenario. This means the gateway periodically requests a 2x temperature reading from the IoT devices. The RIOT network stack architecture follows a recursive design that easily allows for stacking and exchanging protocol layers. In our configuration, we use the GNRC network stack, which provides 6LoWPAN, IPv6, UDP, and CoAP. We extend CoAP with the CoAP proxy and caching functionality, and then we integrate the external libOSCORE package. CCN Lite provides NDN and directly communicates with the MAC layer and the application. In our first analysis, we look at the packet structures for each message type of all considered deployments. We have to keep in mind that we are using a radio technology that is optimized for long battery lifetimes. This means we have a low bandwidth and higher latencies. Another constraint is a maximum frame size, which is limited to 127 bytes. Any frame that surpasses this limit has to be fragmented, for example with the 6LoWPAN adaptation layer. Any additional packet overhead generally increases the packet airtime and makes transmissions more and more prone to packet loss. For comparability reasons, we configure each deployment with the same security algorithms, which is AES 128 in CCM mode and 8 bytes for the message authentication code. We first consider the packet sizes for CoAP without any security measures and observe a MAC header size of 23 bytes. IPv6 with 6LoWPAN uses 35 bytes, the UDP header consumes 6 bytes, and the actual CoAP request message uses 18 bytes. For the response, we observe similar sizes, but the CoAP part reduces from 18 bytes down to 9 bytes. This reduction for response messages comes from an optimization of CoAP. Responses do not include the resource endpoint URI that is in the request. Instead, they use a 2-byte token to match the corresponding request. CoAP with OSCORE increases the request message by 14 bytes, including the structural overhead for OSCORE and the message authentication tag for an ensured integrity. In contrast, the response message increases only by 11 bytes due to an optimization of OSCORE to reuse the same nonce for its AES operation in requests and in responses. The nonce is therefore omitted from the response message and implied by the requester on reception. Our proxy configuration uses a proxy URI string option within the CoAP header of the request to designate the proxy endpoint. This option is only included in the requests for intermediate hops and increases the requests by roughly 40 bytes. The request on the last hop removes the proxy URI option and therefore yields the message size of a typical CoAP message. Interestingly, since we are using linked local IPv6 addresses for proxied requests and responses, 6LoWPAN is able to remove the source and destination IP address completely from the message. The linked local IP address is then derived from the MAC address. The secured variant behaves very equivalently and additionally includes the message overhead of OSCORE. We now move to the NDN setup. Because NDN replaces the network layer, we do not see a packet overhead related to 6LoWPAN or UDP. The MAC header counts 23 bytes like the previous CoAP deployments. The interest and data packets show smaller packet sizes compared to the unsecured CoAP case, and interestingly, the response in NDN is larger than the request. This is because NDN reflects the content name that is present in the interest message back in the response message. In the secured NDN setup, we add security measures to response messages and observe a message increase of 46 bytes. Our main takeaway from this dissection is that the stateful CoAP proxying actually can reduce header sizes for en route messages. In our next evaluation, we measure the completion time for all content requests across all sensor nodes. This means how long it takes for a request to be satisfied with a response. We already know from our previous experiments with the 15.4 radio that we can expect completion times in the range of milliseconds. CoAP and NDN also use a retransmission mechanism, and we configured 5 retransmissions with a 2-second timeout between each of them. If a request is not satisfied within 10 seconds, it times out. We first consider the unsecured protocol variants. NDN is able to satisfy close to 60% of the requests in the sub-second range. Retransmissions were able to recover lost messages within 10 seconds, so that NDN ultimately shows a reliability of almost 100%. Next, we see the performance for our plain CoAP deployment. The first configuration is CoAP None, which is a CoAP deployment without any retransmissions. We observe for the setup that below 80% of requests are satisfied in the sub-second range, and the rest is unrecoverably lost. The CoAP Con setup is performing end-to-end retransmissions, which also reflects on the staircase pattern of the plot. This deployment recovers lost messages and increases the overall reliability to above 80%. The CoAP minimum proxy deployment is doing stateful forwarding and hopwise retransmissions as NDN, but does not deploy caches. We see that this setup generally performs worse than the plain CoAP deployment because of the added network stress due to unneeded request retransmissions that is happening on all hops. If we add the missing ability of doing hopwise content replication, then we see completion times that are very similar to the NDN deployment. This CoAP proxy deployment yields a reliability of close to 100%. With enabled security features, the results look generally a little bit worse because of inflated message sizes. NDN and both plain CoAP deployments show, however, similar results as before. The CoAP minimum proxy deployment without caching is not able to recover the increased amount of lost messages. Additionally, lost messages multiply the number of retransmissions greatly, which then again leads to more packet loss due to the increased retransmission load that applies in parallel to the periodic requests. Here again, adding the content cache functionality boosts the reliability up to the level of the NDN deployment. Our takeaway for this evaluation is that a CoAP deployment with similar information-centric properties yields a similar reliability as the pure NDN deployment. In our next evaluation, we take a deeper look at the actual link stress in the topology for each deployment during the course of the experiment. In the plots, the links are grouped and sorted by the distance to the gateway from left to right. For the NDN setup, we see an increased number of requests and responses for links that are closer to the gateway, which is expected due to the chosen tree topology. The number for requests is also higher than the number for responses, which is also unsurprising because of the request retransmissions. The plain CoAP deployment without the retransmission functionality shows an overall link stress that is much smaller. CoAP with end-to-end retransmissions displays much more link stress. Interestingly, the number of requests is much higher than for NDN, and the number of responses is lower. The CoAP minimum proxy setup with hopwise retransmissions and no caching shows the most overall link stress so far, which is consistent with our previous reliability analysis. The amount of request retransmissions increases greatly, while the number of successfully returning responses is unacceptably low. If we now add the caching ability to this deployment, then we see the same results as for our NDN setup. We show with this analysis that the combination of stateful forwarding, hop-wise retransmissions, and content caching on intermediate hops reduces the overall link stress in multi-hop topologies. In our last evaluation, we analyzed the nodal packet loss and cache utilization of the secure protocol variants for NDN and the CoAP proxy deployments. Each matrix is arranged like displayed in the legend in the bottom left corner. The producer nodes are numbered from 1 to 12 and placed from left to right on the x-axis of each matrix. The y-axis shows the request path from top to bottom like displayed in the topology tree in the top left corner. First, we look at the request loss for NDN and CoAP proxy and observe a comparable behavior. Request losses are more likely to happen on links that are situated closer to the gateway because they are used more extensively due to the tree structure and the converged cast traffic pattern. CoAP proxy shows up to 25% requests getting lost on the topmost row of the matrix, which represents the links that connect directly to the gateway node. NDN, on the other hand, displays slightly less request losses with up to 20%, which is expected because of smaller request packets. On the other hand, our NDN configuration yields larger data packets compared to CoAP proxy because of the signature and the full name that is mirrored back in the data packet. And this is reflected in the nodal loss rates. NDN shows slightly more response losses across the whole network. In our setup, cache hits appear for request retransmissions. Since we observe slightly more response losses for NDN, we naturally observe more cache hits for retransmitted requests in the NDN setup. We have seen in the earlier evaluations that both setups yield a really good reliability with a success rate of close to 95%. Nevertheless, we also observed in this evaluation that we actually experience request and response losses. And the intention of this analysis is to support our previous statement that cache hits successfully shorten request paths and recover response losses. We highlight 3 takeaways from our comparative performance study. First, we can build an information-centric web of things using CoAP standard features. Second, stateful forwarding and hopwise content replication by using CoAP proxies along a request path improves reliability for CoAP. And third, the presented CoAP proxy deployment provides an early deployment chance for ICN principles in existing IoT infrastructure. And this leads us to our future work. With this CoAP setup, we can see how well CCNX and NDN-based forwarding and caching strategies could be reused in CoAP. We also plan to look at the multicast capability of this setup. Thank you for listening. We support the recent ACM initiative to reproducibility. For this, our experimentation code and data are publicly available at this GitHub URL. All protocol implementations are part of the free and open source IoT operating system RIOT.